Video is for problems 7 and 9 on the AP Light Energy worksheet. All right, so after watching these videos, you should be able to do problems 8 and 10. Okay, so first of all, it says calculate the wavelength of a wave. Okay, so we know that we have this equation that goes speed of light equals the wavelength times the frequency. Okay, but that doesn't have energy in it. Well, we also have this equation with energy in it that says energy equals Planck's constant times the frequency. Okay, so we have two equations, except both of them don't have everything we need in them. We needed an equation with wavelength and energy in it, and there isn't one. But what they both have in common is frequency. All right, so what we can do is we can figure out what frequency equals in terms of the speed of light. And so we can rearrange this equation, this speed of light one, and we can get that the frequency is equal to the speed of light divided by the wavelength. And then what we can do is we can substitute into the energy equation what frequency is equal to. So we can get that energy is equal to Planck's constant times the speed of light divided by the wavelength. And that basically is just putting these two equations together. Now, once we have that equation, we want to get wavelength. And so see how energy is on the top, but wavelength is on the bottom, but they're on opposite sides of the equal sign? Well, a little algebra trick is if something is all in multiplication or division, if it switches from one side of the equal sign to the other, it just moves diagonally. So what we can do is we can just rewrite this equation and get that wavelength is equal to Planck's constant times the speed of light over energy. Now we can just plug in our numbers. Okay, so wavelength will be equal to Planck's constant, 6.62 e to the negative 34 joules times seconds. Okay, times the speed of light, which is 3.0 times 10 to the 8th meters per second. So sometimes they write that meters seconds to the negative 1, which means meters per second. Okay, and we're going to take that all over the energy, which is 3.5 e to the negative 11 joules. And if you notice, joules will cancel and the seconds will cancel, leaving us with meters. And so when we do this problem and we get our wavelength for problem number 7, it ends up being, let's see, 5.7 e to the negative 13, I think if I can read my own writing, e to the negative 13th meters. Okay, but a lot of times when they want wavelength, they want nanometers. So you could do a nanometer conversion by saying 1 meter equals 1 times 10 to the 9th or 1 e to the 9th nanometers. And if you do that, you end up getting 5, and I don't know how I got this, but 5.7 e to the, let's see here, that's going to be negative 6, and that's going to be nanometers. Okay, problem number 8 or number 9. So you try 8. You can pause the video and try 8 if you want. Okay, number 9. It says excited helium can emit photons with a wavelength of 185 nanometers. How much energy would 35 grams of excited helium atoms emit? All right, well, we're going to assume something on this, and we're going to assume, and this may or might not be the case in real life, but one atom, we're going to say, is going to emit 1 photon. We're going to limit it to that. We're going to assume that. Okay, so anyway, what we would have to do first is know that on number 9 that we have 35 grams. So we have 35 grams of helium. Well, what we can do is we can actually figure out how many atoms that is by going 1 mole helium, looking up the molar mass, which is 4 grams helium. And then we could say in 1 mole helium, there are 6.02 e to the 23rd atoms. Okay, we're not going to stop there though. We're going to keep on going. And we're going to say that one atom, okay, in one atom, it's going to emit one photon. All right, and then here's what we got to figure out. In one photon, how much energy is there? How many joules are there? Okay, well, you can calculate the energy of a photon is equal to Planck's constant times the frequency. Okay, but we don't have the frequency. Okay, and so we can go back to our speed of light equals wavelength times frequency, and we can actually get that the frequency is equal to the speed of light divided by the wavelength. Okay, so now we can just combine these two together by substituting that in, and we get energy equals Planck's constant times the speed of light divided by the wavelength. So the energy will equal 6.62 e to the negative 34, that's Planck's constant, joules times seconds, times the speed of light, 3.0 times 10 to the 8th meters per second, divided by the wavelength. Oh, the wavelength though is in nanometers. We got to change that to meters before we use it because it has to match our units down here. So in 1 meter, there's 1 e to the 9th nanometers. And so basically that's going to be 1.85 e to the negative 7th meters. So we put that down here for our wavelength, 1.8 e to the negative 7th meters. Okay, our meters cancel, our seconds cancel, and we end up with joules if we do this math. So that energy would equal 1.07 e to the negative 18th joules is what I got. So now I can take this number and I can plug it in right here. So that's how much energy one photon has. And I can do all that math, and I end up getting 5.64 e to the 6 joules. 5.64 e to the 6 joules is the answer. Okay, that's it for that video. Why don't you try number 10? See if you can do number 10. Then you can check your work. I posted it on the Google Classroom under the light energy calculation module. That's it.